suppose we're given this function. And what is the value of this function when x is equal to 0? 0 substitute here will be 0 minus 1 divided by 1. It will be -1. Very good. How about at x is equal to 1?
0.
Yes, 1 squared minus 1 equal to 0 divided by 2. It will be 0. Very good. Use your calculator and compute the value when x is equal to 10. And round it up to 6 and decimal places, please.
.9801198.
Perfect. Thank you. Who was that? Elijah. Oh, yeah. Thank you. Perfect. Thank you, Elijah. So how about at x is, so at -10, because here x will be square, right? X is square. So +10 or -10 will give us the same value. Bless you. And the same things for plus and -1 and etc. How about at x is plus or minus 100? What is it? Okay.
0.9998.
Thank you. Very good. So we see that. And how about 1000? Do one more step. Okay, I provided the result here. We see when x becomes very large, going to infinity, then it will come closer and closer to what? 1. Thank you. Very good. So we observe this, right? And here is the graph of this function. The green lines here is the graph of this function. And the horizontal line when y is equal to 1 is the red line here, is the limit. When x approaches go infinity or -infinity. So when x becomes very large, f of x will come closer and closer to this value. So we call it the limit at infinity. Okay. So here is the definition of it. If x go to a limit of f of x when x go to infinity, if it approach a specific value, we call it L, then this is the limit at infinity. The definition, or we sometimes say fx approaches L is x approaches infinity. There are different situations. For example, here. Yes. Yes. So we call it the horizontal asymptote. Okay. So here, L, y is equal to L, we call it the horizontal asymptote. Okay, just a name for the red line here. Very good. And there are different situations. So in the first case here, when x becomes very large, f of x approach this line here, right? This is another example below this value, or it may approach above and it come closer and closer to y is equal to L, right? Okay, no problem, Andrew. Then the next one, the next graph, sometimes the f of x is below this horizontal asymptote, sometimes is above the horizontal asymptote, but as x approaches infinity, it comes closer and closer to L. This is another situation, okay? They are both approaches approaching the limit y is equal to L. Similarly, if x goes to infinity and limit of f of x approaches L, we call it another infinite limit. So for any given function, how many horizontal asymptotes do we have in general? Yes, or sometimes we may have two, right? If x go to infinity, approach to 3, for example, and limit of f of x when x go to negative infinity, somehow it approach 0. This is another horizontal asymptote. So therefore, at most, it has 2 horizontal asymptotes. For some specific case, it had just only 1 horizontal asymptote. But there may have so many vertical asymptotes, right? Do you remember? Give me an example. Tangent, very good, thank you. Tangent or cotangent. They have so many vertical asymptotes, right? Okay, very good. That is simply a new concept. Or here, now let us play with some specific example. Okay, the definition here is called horizontal asymptotes. As long as if this limit approaches L, or this limit when x approaches negative infinity is also L. Now let us play with this example. Find the limit when x go to infinity of the function f 1 of x here. Let us call the function f of x is 1 over x here. When x is equal to 0.01, what is f of x? Very good. How about at 0.1? Very good. How about at x is equal to 1? Very good. At x is equal to 10? Yes, 110 or 0.1, very good. At x is equal to 100? Very good. So let us plot these points, right? This is a basic function. Remember the graph of this guy? You just draw it one time. So suppose here is 1, 1, right? Or let me just draw right here. I'll just put it here, it's fine. 1. Then the point 1, 1 belongs to the graph here, right? And x is equal to 0.1, it should be somewhere here. Then y will become very large, it will be somewhere here. It's not a good draw, but imagine is like this, the one range when x is positive, right? When x comes close to 0, this guy goes to infinity. When x goes to infinity, this guy goes to 0, right? How about the branch when x is negative? Very good. Every output will be negative, or in other words, this guy will be flipped, right? Somehow like this. This is the graph of the function f of x is 1 over x. Okay. So according to the visualization and some computation here, what is the limit of the function fx when x approaches positive infinity? Yes, very good. How about the limit when x approaches negative infinity? It's also 0, right? Very good. Therefore, what is the horizontal asymptote of this function? Yes, this line, the OX axis as well, right? Horizontal asymptote in this case. Now, play with this. How about the function g of x is equal to 1 over x plus 1? How does it look like? So every value of x, the function f of x previously, we'll add 1 here, right?
All the y values for 1 to 6 here up.
Very good. All the y's value will be shifted up 1 unit. Do you see how it is shifted? So let us play with this. The decimals, it will shows you 1 over x here. So at home, you see how it behaves easily. Plotted here. The red function is the graph of the function 1 over x. And here, 1 over x here, if we add 1, the function will be shifted up 1 unit. And what is the horizontal of the second function?
1.
Yes, the horizontal now in this case is 1. How about if another function, it is 1 over x, subtract 2? Go down 2 units, right? Very good. So this is a very interesting properties of a graph, okay? Now, how about this guy? Okay, let me replace this by 1 over x minus 1. How does it look like?
Your x values are shifted.
Yes, the x value is now shifted to the right-hand side 1 unit. You see it? Okay. Originally, the function 1 over x is undefined at x is equal to 0. In the second function, it is now undefined at what? At 1, right? And it is shifted to the right 1 unit. Okay, very interesting properties. Just play with this, then you understand how a function is shifted here. Another example, if we're given, this is a very common function, x squared. How about x squared plus 2? Guess, how does it look like?
X values will shift.
Will be shifted up 2 units, right? Very good. Okay. How about x minus 1 square? Yes, it moved to the right 1 unit, right? These are very interesting properties of the graph of functions. Play with that. Okay, now go back to our section here. Let us continue. So we have the theorem here, rational numbers. The limit of 1 over x to the r, where r is a positive number, strictly positive. The limit when x goes to infinity of this function is equal to 0. Okay. Oh, sure. Is it better now? Mm-hmm. So now let us use this theorem. Similarly, if x go to negative infinity, the limit of this guy is also equal to 0. Then let us play with a second example, limit of this guy. Try it yourself first. Write it down on a piece of paper. Sorry, I will zoom it in a little later. Okay. Now compute this and indicate which properties of limits that is used each stage. First, what is the highest degree of the numerator? Very good. And the highest degree of the denominator? Good job. So look at this. If x is equal to 10 to the 3, what is x squared? It means we are comparing 1,000 to 1 million, right? So which one is bigger? Between these two guys? Yeah, 10 to the 6 is a lot bigger, right? It means that even here in this case, 3x squared minus x minus 2. When x is very big, it is somehow similar to 3x squared. Right? Similar. So these guys, we can ignore them. It becomes very small. Okay. So that is why for these, we only care about the highest degree of the numerator and the denominator. Okay. So in order to find the limit of this guy, so we see that if x becomes very large, the numerator will be going to infinity and the denominator is also going to infinity. We cannot compare the two of these, right? So what should we do to get rid of this? So if you go home, look back here in the slides, I indicated here. To evaluate the limit at infinity of a rational function, we first divide both numerator and the denominator by the highest power of x. That occurs in the denominator. Okay? And we always assume that x is not 0. Anyway, in our case, then we apply that properties. Okay, we compute the limit of 3x squared minus x minus 2 of 5x squared plus 4x plus 1 when x approaches infinity, and the highest degree of this denominator is this guy. Therefore, we can write it as limit when x approaches infinity of the numerator divided by what? Very good. We divide it by x squared. If we divide the numerator by x squared, we also need to divide the denominator by x squared, right? To make it even. Otherwise, it's changed to a different thing. Now, look at the numerator. Is it clear why we do that in this step?
Cancel out.
Very good. Then now, in the numerator itself is a fraction, right? The numerator of this small fraction here involve subtraction here. So we can separate them into 3 different smaller fractions here. So it will be subtract what? Very good, thank you. And the denominator? Yes. This is fraction properties. So now it becomes a new thing. Can we cancel it? Three x squared divided by x squared, it will be? Very good, 3. Subtract what? Yes, look at this. X squared is x times x, right? And in the numerator, you can always imagine that, okay, x is equal to x times 1. Then once you cancel x here with the 1x below, then 1 is left. Then it is 1 over x. Very good. Similarly, here we just leave it here, 2 over x squared. And the denominator is 5 plus, what is it? Next. Very good. Okay, nice. Now, when x goes to infinity, can the denominator becomes 0? It's always non-zero, right? If x goes to infinity, the denominator, I mean the whole thing's here, is always different from 0. So which limit properties should we use here? Quotient of a fraction. So let us break it into the limit when x goes to infinity of the numerator, which is 3 minus 1 over x here, minus 2 over x squared, and the denominator is the limit when x goes to infinity of 5 plus 4 over x plus 1 over x squared. Now, so the limit law for quotient, right? Next step. What should we do with this? Okay. Here, which limit loss should we use? Very good. Subtraction. It will be the limit when x goes to infinity of 3 minus limit when x goes to infinity of 1 over x minus limit when x goes to infinity of 2 over x squared. Very good. Limit when x goes to infinity of 5 minus limit x goes to infinity of 4. Oh, this is plus 4 over x here plus limit 1 over x squared when x approaches infinity. What is the mistake of my writing here? The mistake is right here. The equality, we should write it here in the middle of this line. Otherwise, it confuses reader. Okay, be careful. Okay, good job. Then we compute each of the limit here. The limit of a constant will be a constant, right? Then in the numerator, it becomes, thank you, 3 minus, yes, minus 0 and minus, yeah, 0 again. We applied the theorem before. Limit of 1 over x to the r will be 0 when x approaches infinity. Very good. And the denominator? And finally, it will be? Very good. Nice. So after solving this, we look back at the, yes.
So it's 0 because that would be the horizontal asymptote for each of the equation.
So you can think of this way. When the numerator is fixed as a constant, then x goes to infinity, the denominator will be
0.
very big. And a number divided by a very big number, it comes to 0.
Yeah.
Yeah. Very good. So look at, so it's very interesting that the result of this limit is exactly the coefficient here, 3 over 5, right? So once we know the highest degree, we can guess. Okay, very good. Yes.
What if the limit was x to the negative infinity? Would the number be different?
If you mean the limit when x approaches negative infinity,
Yeah.
the limit of that will be also negative infinity. Because imagine, okay, it will be, suppose we substitute 1 divided by negative 10,000, for example, it will be negative 0.0 something, right? Still small. Still be 0. Or, yes.
So if we were like when we encounter limit questions on the test, would you like the answer in a full sentence conclusion form, or are we just boxing that in as our answer? Like if we have limit questions, like how in the quiz you had a conclusion part, would you like that to be a one complete sentence?
It doesn't necessarily to be a complete sentence, but you write a quick conclusion yourself. For example, it does not exist. You can simply write, therefore it does not exist.
Okay.
Or use notation does not exist. I'm okay with that. Just make it simple. You don't have to write a full beautiful sentence. As long as you prove that you understand, that's it. Okay, is there any other question? We good? Okay, let us play with another example. Okay, limit. Of the function f of x as x approaches infinity and f of x is square root of 2x squared plus 1 and 3x minus 5. Or in the slice, this is the example we are doing. Find the horizontal and vertical asymptote of the graph of the function, of this function, right? Very good. And yeah, let me just replace this by f of x here. Okay, now first, in order to find the horizontal asymptotes, what should we do? Another way to ask, it means that we need to find the limit when x approaches infinity of f of x, right? We rephrase this by mathematical notation. X approaches negative infinity of f of x. Okay. And what is a vertical asymptote? Very good, thank you. Is it Marissa? Thank you. It means that and what is it in this case? Yeah. Then it means that we need to compute the limit of this function as x approaches 5/3 from the right hand side, right? And we also need to find the limit of f of x as x approaches 5/3 from the left hand side. This is another way to understand the question. We need to do these things. Let us do step by step, okay? Is it clear what we are asked and what we should do? Very good. Now let us start solving this. Now, therefore, let us compute the limit when x approaches infinity of this function, which is square root of 2x squared plus 1 divided by 3x minus 5. What is the highest order term of the numerator? Interesting. It's tricky. The highest degree of this is x squared under the radical sign, right? But then remember, the radical sign is also the order of this guy. Therefore, we should count it. Or it is this guy, it is a number times x squared, right? Can we break it out? What is it? Yes. Very good. So it means it is the order of square root of 2, and then square root of x squared gives us absolute value of x, right? And, or in other words, the highest degree of this is of the order 1. Okay? What is the highest degree of the denominator? 1. Very good. Now, remember, again, square root of x squared is absolute value of x, or it will be x for what? Yes. If x is positive, then square root of x will be absolute value of x will be x. And if x is negative, then absolute value of x is negative of x. So it is very tricky. So when we compute the limit when x goes to infinity here, it's easy, right? Therefore, we have and we are recommended that, okay, in order to compute the limit of this guy, we can do it by dividing both numerator and denominator by the highest degree, which is x in this case, right? The highest degree of the denominator is this guy. And here 3x minus 5 divided by the highest degree, which is x. Okay. Are we good here? Then, because we're computing the limit when x goes to infinity, or in other words, this is positive, right? Then we can replace x by this guy. Is it okay? Replace x by square root of x squared. Okay? Do you all see what I mean here? So since we are computing x goes to infinity, if x goes to infinity, it is positive, right? then we know from this, x, if x is positive, then we can replace x by square root of x squared. Because in the numerator, we have the square root here. And we simplify the denominator here. What do we have here? Okay. Is it clear up to this step? Yes.
Why aren't we substituting that?
Yes. We substitute this here because in the numerator, there's a radical term.
Yeah.
If we replace x by this guy, then we may somehow able to cancel this guy to each other.
Right.
Since the radical properties, we know that square root of something divided by square root of something, it would be the square root of the fraction, right? Which is 2x squared plus 1 divided by x squared. Okay?
So now,
Yes, now inside the radical sign, we'll simplify it, okay? What do we have?
2x squared is x squared.
Very good. It will be 2x squared over x squared simply give us 2, right? Yeah, I haven't write it yet, but yes, you're right. 1 over x squared and the denominator here. Okay. Then we apply the limit of a quotient first, then apply the properties of a limit of a radical sign. We put the limit inside, right? Okay, go home and try to write it step by step, and we'll see each other tomorrow.